Welcome protein coders, let's build some coding muscles. Today we're gonna see bipartite graph. What is a bipartite graph? A bipartite graph is a graph which we can divide in two sets, in which in every set we should not have any adjacent neighbors. Okay? And to check this, we use an algorithm called two-color algorithm, in which we color every neighbor of the adjacent node by a different color. So let's look into the graph 1. Let's color the node 0 with blue, 1 with red, 2 with blue, 3 with red. So you can see no adjacent node have same color. So it's a bipartite graph. Now let's see in the graph 2. Let's start coloring 0, 1 with red, 2 with blue, 4 with red, 3 with blue. Here also you can see no two adjacent node have same color. So it's also bipartite. Now let's see in the graph number 3. 0 is blue, 1 is red, 2 is blue, but here at 3 is neighbor of 1 and 2. So it can be red also or blue also. So it's not a bipartite graph. So from here we got a very important observation. If a graph has odd length cycle, it can't be bipartite. Now let's see how we wanna check a graph is bipartite or not using DFS. Let's have a color vector which is initialized with -1. Okay, that means no color. Let's say for color blue we will write 0, and for color red we will write 1. And if you see carefully, if the color is -1, that means the node is not visited. So we can use this same color vector as our visited vector also in our DFS. Okay, so we will keep this in mind. We will not use any extra visited vector. So let's start doing our DFS from node 0. So let's mark 0 with blue, and then we will move to its neighbor 1, mark it as 1, then 2 will mark 0, 4 will mark 1, 5 will mark 0, 3 will mark 1. But see, at 3, then its neighbor 1 has also color 1. That means both are red. So we will return false in our DFS. Okay. So from here we got a very simple condition. If a neighboring node is not visited, that means color of neighbor is -1, or else if it's visited. So if it's not visited, we will simply call DFS and color the neighboring node with the opposite color of the parent node, which is 1 minus current color. So let's say if our current color is blue or 0, then the neighboring node will be 1 minus 0, which will be 1. Okay, and if our current node color is 1, that means red, then 1 minus 1 will be 0. It's opposite of it. So we can switch colors by using the simple trick. Or else if our node is visited, then we'll check if the color of neighbor is equal to color of parent, then we'll return false. Okay, now let's see how we're gonna implement this in our code. In our function, we will have our starting node, color vector, current color, and also our adjacency matrix. Now let's first color our node with the current color. Okay, simple. That means our node is colored and we have also marked it as visited. Now we will traverse our simple DFS code. Okay, we'll traverse in adjacency node, and if our neighbor is not visited or it's not colored, we will simply call our DFS and color it with the opposite color. So we'll pass 1 minus current color. Okay, or else if it is visited, that means it's colored, then we'll check if the neighboring node color is equal to the node color of the parent, then we'll return false, and at the end we will return true. Okay, now let's see in BFS how we're going to do it. It's very simple to observe. We'll mark 0 as blue, then 1 is red, then 2, 3 as 0, and 4, 5 as 1. We'll go level wise and mark the neighbors with the opposite color of their parents. But here see, at the end we got two same coloring nodes which are adjacent, so we'll return false. Right? Now let's see in the code. We will first mark our starting node color. Right? We'll color it with 0. Then we'll push this into the queue and we'll start our BFS. It is simple BFS code with slight modifications. So what we will do is we will first pop out our node, right? Then we will check for its neighbor nodes. So for every neighboring node, if it's uncolored or color of neighboring node is -1, that means it's not visited or not colored. We will simply color it with the opposite color and push it into the queue. Else if it is colored, then we will check its color with the color of the parent node, and if they are same, we will return false. At the end, we will return true. Okay. Now let's revise what we have studied today. We studied what is bipartite graph. A bipartite graph is a graph in which we can divide it in two sets, in which in each set no two nodes have edge. Okay. For this, we use a two-color algorithm, and in graphs with odd cycles, we can't have bipartite nature. Okay. Then we saw how using DFS we can find out the graph is bipartite or not. If the neighboring node is uncolored, we will color it using DFS. If it is not, we will check the color of the neighboring node with the parent node. If they are same, we will return false. Right? Simple DFS with a slight modification. Then we saw the code for it, and while coloring using DFS, if it returns false, we will return false. Right? Just a slight optimization. Now we saw how to color graphs using BFS. It's very similar to DFS. Then we saw the code for it. We wrote simple BFS code, right? We will color the starting node, we will push it into the queue, and we start our BFS. In the BFS, we'll get the node, we will pop it out from the queue, and then we will traverse for its neighbors. If the neighboring node is not visited, we will color it with opposite color and push it into the queue. Else, if it is colored, we will check it with the parent color. If they are same, we will return false, and at the end we will return true. So that's it from my side, guys. Thank you for listening. If you have any doubts, please mention them in the comment box. You will find the problem and the solution link into the description box. If you don't understand, don't like, don't subscribe, but if you do, please show some support. Keep smiling, keep practicing. Thank you.